And welcome everybody. Can you hear me well? Is that fine?
Yeah.
Great, good. So as soon as I get control, I will start off with the vertebrates. Okay. So welcome everybody to the taxonomic session on vertebrates. My name is Pascal Malkemper. I'm currently in Vienna. And I would like to start with a quick overview of this whole project, what it's all about. Just quickly, because I think most of you already heard this at least once or twice. So it all started with a request from BugLife. Can you see this? Yeah. So it started with a request from BugLife asking the question to Eklipse. Can you please summarize what's known about electromagnetic field effects on wildlife? And Eklipse then assembled or did a literature screen on recent peer-reviewed studies, newer than the year 2000, with a very restricted focus on wildlife studies. So we already heard that studies on human health were excluded, as well as studies including domestic animals. Most of those studies were excluded, for example, also lab rats and mice. And the EMR range was very restricted with the exclusion of light, but also of very strong static magnetic fields, such as MRI exposure was also excluded in this study. And the literature search identified roughly 150 publications, out of which 2/3 were used then for the later analysis. And the analysis was done by a multidisciplinary steering committee, which consisted of 6 experts, 4 from the biological sides, according to different taxonomic groups, and 2 technical experts dealing with, for example, the exposure measurements and the EMR ranges. So we then produced an analytical grid in which we listed the information about the different studies that we analyzed. So we listed whether which taxonomic groups were dealt with. We listed the EMR ranges in terms of frequency range, but also in terms of application-specific exposure, if it was just identified as a power line magnetic field, for example, or as a mobile phone field. We additionally wrote down whether we had field or lab studies, so whether studies were conducted. And then the main part was that we analyzed the quality of those studies in terms of both technical aspects and biological aspects, and rated them according to this rating system that you see here, from 0 being of insufficient quality, so not meeting scientific standards, to up to excellent quality, being the best that you can think of. And finally, we would then summarize the main findings and try to identify the most important knowledge gaps that are still open. And today, I would like to give you a summary about the findings on vertebrates. And this will not be a comprehensive summary, but I will give you a quick summary and highlight a few examples that I think are really important. And so the group of vertebrates is a very diverse group, including groups such as fish, amphibians, reptiles and turtles, birds and mammals, also including humans, which we will not deal with today. And given this high diversity of animals, it was actually astonishing that the number of studies, that were found that specifically dealt with this very specific topic was quite low. So we included 37 studies, which included already 16 reviews, which also, of course, dealt with studies older than the year 2000. And in terms of technical aspects, to sum it up, it was a bit disappointing that the technical quality was also quite low. Almost half of the studies were of insufficient or minimal technical quality, and only 35% of the studies reached an excellent quality rating. And the most common reasons for this were that, and this is something that is not specific to EMR, but that seems to more often happen with EMR studies, is that the blinding was not properly done, so that the experimenters did know the conditions when they collected the data, This is a problem with magnetic fields, obviously, because we for ourselves cannot really control for this. The second thing, and this is also a problem in ecological studies in particular, was that no proper controls, so sham controls, were conducted. And a third thing that already was mentioned during the plant session, I think maybe or even before that, is that we don't have standards for reporting the electromagnetic exposure or measurements of the electromagnetic fields in a standardized way. And this is missing, and this leads to a lot of studies where you can't do proper replications because the AMR properties were not adequately described. So these were the technical aspects. Coming to the biological aspects, it looked much better. Almost half of the studies were ranked excellent. Another 35% were ranked good, meaning that there was a clear hypothesis that had been tested. There was an approach which was appropriate to study the hypothesis, and the data then yielded conclusive results. The most frequently studied groups were birds and mammals, and I will return to two examples, including birds, later. The most common issues for the quarter of studies that had insufficient or minimal biological quality, the reasons were mainly that there was no specific hypothesis tested in terms of mechanistical aspects in most cases. So there was just tested, do we find any effect? And then you, of course, have high for type 1 errors. If you just test for any effects and you test not really specifically for hypothesis. And the third issue was that most of the time the ecological consequences were completely unclear, but that's something that cannot be solved very easily, but we come to that. So let me first start with an example of what I think is an excellent series of experiments which highlight both the very interesting results with direct ecological consequences, and on the other hand, the problems associated with those studies that I've just mentioned. So this example is about house sparrows. You might have noticed or might have not noticed that there's a strong decline in house sparrows in several European cities since the mid-90s. And several explanations have been stated for this. And the authors of a series of studies of two different labs had the hypothesis that EMR was responsible for this decline. And what they did is they went out into the cities, sampled the density of sparrows, and in parallel did EMR measurements. And they found this quite strong correlation, negative correlation between sparrow density and the field strength of the electromagnetic field. And this is a very interesting fact, which would show that there's a direct ecological consequence, mainly the decline of a species in certain areas with high electromagnetic field radiation. But on the other hand, this really highlights the problems that I've just mentioned, which is that there's no blinding. So the measurements of the EMR and the species was done at the same time by the same person. And in addition, and the authors totally acknowledged that, so I'm not blaming anyone here, it's a very interesting study, but in addition, other factors could not be monitored, such as food abundance, air pollution, and other species that might have different between different areas that have been studied. So this is a really interesting indication, but there's a big but. We don't really know if that's really an electromagnetic field effect. But I will come to another study later that might support this. So this is basically my summary slide for the results on vertebrates, which was again a bit disappointing for vertebrates other than birds. 50% of the studies are like pro effects of EMR fields, 50% are against the effects. So in absolute terms, we don't really know. It's unclear whether there are effects on other vertebrates, other than birds. But in birds, specifically, there are more studies reporting effects than studies reporting no effects. And so the main findings I list below are mainly focused on mainly results from birds, which are behavior changes, as we've already seen, that EMR avoidance, disorientation in EMR. I will come to an example here later. Memory deficits have also been stated in rodents. Developmental abnormalities and decreased reproduction, increased mortality could also be a reason for the sparrow effect, for example. And physiological responses have also been reported, very interesting ones on the opioid system that seems to be happening in invertebrates, from snails to vertebrates such as mice. But the big problem, and that's why I'm not going into detail here any further, is that most of these effects miss independent replications across different labs. And I want to use an example to highlight why this might be the case, and to give an idea of how we might overcome this. So this example relates to something that has been said before. The biggest problem we have is that we don't really know how electromagnetic fields might interact with biological tissue. We don't know the transduction mechanism. And for weak magnetic fields, strong magnetic fields, they create heat, and this heating up of tissue is, there's no issue about that. There's no discussion about that, that influences biological systems. But the electromagnetic fields in the environment, in 99% of the cases, are too low to create heat. So in this case, we need a different transduction mechanism if there is anything happening in biological systems. So I want to use this example of a sound problem, which is the discussion whether or not mining noise has deleterious effects on whales. And if we would think how we could study this, we could basically go out in there and monitor whales close to the mining stations and try to correlate this with sound emanated by those mining stations. But again, we would have an obvious problem of finding a proper control area, right? So how else could we study this? Well, we know that it's sound that's influencing the animals here, and we know that animals have a weak spot, let's say, for sound, which is obviously the ear, which has been shaped by evolution to be most sensitive to sound pressure waves. And having a look at the whale inner ear, we could predict what whales hear. We could have a look at the inner ear if it's damaged by this noise, and we could basically predict which frequencies would affect whales the most. So the idea is that in order to fully assess the effects of any physical stimulus on a biological system, we would need like the weak spot, the transduction mechanism, either if it's a receptor or just any transduction mechanism that's unspecific, but we need to know this in order to really predict the effects of any physical stimulus. And coming back to our vertebrate overview, I've chosen these examples here for a reason, because for all of those animals shown here, it has been suggested, and there's evidence for this, that they have a magnetic sense, which they might use. So they are able to perceive the Earth's magnetic field. And most evidence has been collected, I think you're probably all aware of this, for migratory birds. So they use the Earth's magnetic field to orient during their migratory route, which for this European robin is from northern Scandinavia, for example, to northern Africa. And for these birds, there is quite a lot of evidence that a specific protein in the retina is responsible for sensing the magnetic fields, and this protein called cryptochrome is predicted to be affected by very low intensity radio frequencies. Oh, I just see that my power is going low. What is wrong with the charger here? I hope I'm not gone soon. I'm almost done. So it's predicted to be affected by radio frequencies. And this has been published in Nature a few years ago for a good reason. And so what the people did is they tested in a very controlled way. Can you hear me? They tested in a very controlled way in the lab how those birds oriented when the magnetic field environment was shielded or not shielded. So the whole difference between those two groups you see at the top here, one is oriented towards the migratory direction, the other one is not, is that the magnetic environment was shielded in the frequency range between 0 and 5 megahertz. And this is a very important finding because this is a very low radio frequency background of a small city in northern Germany. And the only thing that really changes between those groups was the radio frequency background. So this shows that the magnetic sense of birds, at least, is affected by radio frequencies, and it can be clearly predicted which frequency range should affect the animal based on the theoretical idea of the magnetic receptor, for which we have some evidence. And if those other animals would use the same or different receptor, and we knew more about these receptors, we could specifically address those frequency ranges and see if they really affect those animals.
Okay, it seems the charger of Pascal has died.
Oh no.
Pascal, are you around? Okay. Well, that's something about our technical virtual web conference. We might have some hiccups like that. So basically what you see is the summary slide. So I think Pascal was actually reaching the end of the presentation. In the summary slide, you can see the different statements, the different aspects that were mentioned by Pascal, and this gives a level of confidence on agreement and on quality of the evidence. So you can see where things spread, and for birds, it's clearly more. It's clearly more on the higher level of confidence for a magnetic sense of birds disrupted by electromagnetic field. And some unresolved as well on the longer exposure and stronger effects are mentioned. Well, when Pascal comes back, we will see if we have time.
Can you hear me maybe?
Pascal.
I'm very sorry for this. The power plug was dead. I don't know what went wrong here. I just changed it.
Okay.
I now have power again. I don't seem to have video. I don't know why this is.
Okay. Well, we are on your last slide on the. You remember the graphic you had. Do you want to? I think it's your last slide,
if you
right?
Can hear me well? I can continue from here.
Yeah.
So I don't know. Did you discuss this slide already? So
yeah. Well, I just summarized that we were looking at the spread between the graphic of the level of agreement and the quality of evidence.
So as I've just mentioned, I think the most compelling evidence exists for the magnetic sense of birds, which is disrupted by radio frequencies. Okay. So this is an established fact, I would say. It's incomplete, because we don't really know if cryptochrome is a sensor, but it is very likely. It's incomplete in the sense that we don't really know the specific frequencies, but we have good predictions for this.
Okay. Can you summarize the last comments in 2 minutes, Pascal, because we are running a bit behind?
I can, but it's not really working. You can still hear me, but I can't control it. That's
okay. So we are on the slide with summary and conclusion, knowledge gaps and research needs now.
Okay.
So you know.
Yeah. So I think, again, to repeat this again, I think the most important thing is that we need to find out how magnetic fields interact with biological tissue. Either it's via a receptor that's specifically designed for this, or not, but it would be highly likely that if there is a receptor across these vertebrate species, that it even exists in non-migratory animals. And if it's still functional, that might give us a hint of how electromagnetic fields could interact with even non-migratory animals. In addition to that, without seeing the slide now, actually I have to say, I think it's really important that more ecological studies are performed, which for a few reasons is really hard to do. As I said, proper controls are really hard to do. But I think a good start would be to start off with meta-analysis, using RF data and combining it with population data, for example, such as GBIF databases and so on and so forth. So using electromagnetic field measurements on a broad scale and combining them with ecological data would be a good start for ecological studies, I think. And then maybe if there is some connection, we can try to do this in a semi-lab environment, like a small outdoor environment where you have controlled conditions, different species, and maybe long-term exposure to see the effects on ecological systems.
Okay.
Yeah, very sorry for this.
No, it's okay. I mean, excellent way to come back and just catch the ball at the same time. Thanks a lot, Pascal, for your reactivity. And
You're
also,
welcome. I will quickly close the program. I'll be back in a minute.